All right. Newton's method is an iterative process. It helps us to approximate a solution when we can't solve it otherwise. All right. So the formula for the Newton's method. F of x sub n plus the f prime of x sub n, x minus x sub n. Because remember, this is the slope. And that's your function value. If you think about it, this is an equation of a line.
It kind of looks like the point slope form.
Yeah, very much so. Yeah, because you have the slope, you have a point here, because it's x minus xn, and then you have this could be the y-intercept. What's that? Mm-hmm.
Chapter 4, section 7.
It is 7.
For the chapter.
Look at an elephant. It's anywhere from chapter 4 to chapter 7. Good luck in finding it. So what we could do is, if we set y equal to 0, what is that going to find for us? Very good. So let's look at this. Let's solve for the x-intercept. So let's solve for x. What's the first thing we do? Get rid of anything added, subtracted. So move this over first. So we get negative f of x sub n equals f prime x sub n, x minus x sub n. Since we're solving for x, get rid of the f prime. We have x minus x sub n equals negative f of x sub n over f prime x sub n. Last step. We have to get x by itself, so we have to add, I have to move this one over. So x is equal to x sub n minus f of x sub n over f prime x sub n. So Newton's method, again, it's an iterative method. This formula, you notice we have x sub n, where n is any number from 1 to infinity. It keeps on going until we find the appropriate solution. So what we have to do first make a guess for the first, remember, we're trying to approximation that solves that. So make a guess that approximates. So it's what you're doing, you're picking the first X and seeing what happens. We're trying to get f of X equals 0. We're looking for solutions. Once we do that, this X we picked, that's our X sub 1. This is our initial guess, our first guess. Well, let's just make it X sub 0 since that's our initial guess. What do we do with it? What we do with that is we plug this inside our formula here. Because what we're doing here is we're looking for our next X value, which that's the formula. This is the xn plus 1. So let's look what happens. If this is X sub 0, this is what n is. If n is 0, this is n. We have X sub 0 minus f of X sub 0, f prime of X sub 0 equals what? What's this going to be? 0 plus 1. So this will, once we plug in 0 here, this will give us X sub 1.
I was gonna say that base is only the number.
Where we go, right? Because once we make the initial guess, the rest is out of our hand. Because now our X sub 1, we plug that in there to find X sub 2. Then whatever we get for X sub 2, plug it in there, that gives us X sub 3. Let's look at an example here. So let's look at an example. Remember, our formula is xn plus 1 equals xn minus f of X sub n, f prime X sub n. Okay, example 1 says, approximate the positive root for the equation. Well, okay, first off, what is a root? Root is the same thing as solution, is the same thing as x-intercept, is the same thing as a factor. These are all relatively the same. These all give us relatively the same numbers. Because remember, what we're looking for here is what is the x value that makes it cross the x-axis? What x gives us the x-intercept? So the function we're using here is x squared minus 2. So our first step, set that equal to 0. We have f of x, which is x squared minus 2. We need f prime of x. Because remember, we need to get the denominator here. So this formula now becomes this. Xn plus 1 equals xn minus xn squared minus 2 over 2xn. That's the formula we're going to use. You can process this like this by making the first guess, or you can algebraically simplify this. Whenever you get this, because this is an x, this is your functions. Usually the best thing to do is to simplify those, make it into a more compound function. So how will we do that? So we want to get this side. What will we do to this side, make it easier? We can't because it's not a perfect square. We could look at, okay, we need to get a common denominator. So we can put 2xn over 2xn. So that's going to give us 2xn squared over 2xn minus xn squared minus 2. We have 2xn squared. This is a parenthesis up here. So it distributes, so it's minus x squared n plus 2. Two xn squared minus 1x squared is xn squared plus 2 over 2xn. You could leave it like that, or you can make it, since we have a monomial on the bottom, you can split it up. Or we could put this under both of these. So the xn's cancel. And the 2's cancel there. And we can make it xn squared over 2xn plus 2 over 2xn. One of these cancel and the 2's cancel. So you can use either one of these two equations. So our first, let me put that on the side. So we have now our formula. I like the first one better. So we have, actually, I like the second one, but it's not squared anywhere. Xn over 2 minus 1 over xn. There's no squares. So the first thing you have to do is come up with your initial guess. What number do you want to start off with? We're looking for x sub 0. What can we not use? We cannot use 0. Because when this is our n, so we're looking for 0 plus 1 equals x sub 0 over 2 minus 1 over x sub 0. So we cannot use a 0 on this initial one. So let's start off with a 1. So x sub 1 is equal to 1 over 2 minus 1 over 1. So x sub 1 will equal negative 1/2.
Shouldn't it be addition and not subtraction?
That's what I was just looking at. Yes, I think it should be. Where's my numbers? My papers. Yes, it should be because I made an addition here. Yes. Good catch. Thank you. So it makes it 3 over 2. So that's where we begin the next one. So that's x1. So now we go to x2, which we have x1 over 2 plus 1 over x1. 3 over 2 divided by 2. Take the top, flip the bottom. This is take the top, flip the bottom. 3 over 4 plus 2 over 3. So we have 9, 8. So we have 17 over 12. Then we do the same thing. So it's x2 over 2, 1 over x2. Over 1. Where's that number? Push. So that's going to give us 17 divided by 24 plus 12 divided by 17 equals 1.4142. Okay, let me check something out here. What was the original function? It was x squared minus 2. One point 4142 squared. Minus 2. Okay, what's going to happen here is now we take each of these numbers and plug them back into our original equation. And this one, what's happening is each one of these numbers we put in there, the values are going to get smaller, 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 smaller. We want to get closest to zero as we can get. And the number of, in this example, what was that one? 1, 2, 3. We had 4, 0. So this tells us how accurate we are so far. So the next time, this is our x3. Okay, let's look at this one. At x2. At f of x2. 17/12. This one equals 0.00694. So you see each step, this is x3. Each step, our number is getting closer and closer and closer and closer to 0. And what we have to do is we have to determine what level of accuracy do we want. How many digits do we want before we're done? We're safe. So this is x2, plug that into your original equation. We get this. X3, we get this. So what do you think is going to happen at x4? It's going to get a lot smaller. You should have, since this one had 2, this one had 4, we're looking at 5 or 6 in the next level. Did you get something different?
No.
So we use these formulas. These are our x values. Once we find the x values, plug them back into our original equation, and we're going to see how small we can get the answer. Okay, example 2. Find the x coordinate of the point where the curve crosses y equals 1. Find x value where this function crosses that horizontal line. Okay, so what do we got to do first?
No.
Yeah, so we have to pick our first, well, we have to do more than that. We first have to find the first derivative, because we have this right now. That's the top. We got to find the first derivative, which is 3x² minus 1. That's the bottom. Where it equals 1. That's f of x. F prime of x is 3x² minus 1. Remember, the x-intercept is finding where? When it equals 0. So even though it's asking for where this one is, we just have to make it to where it's 0. So our formula for our x values will be x³ minus x minus 1 over 3x² minus 1. These are all x sub n's. So now we have our formula. We have our function. We need our first guess. Equals 1 minus 1 minus 1 minus 1. And minus 1 cancels, so it's -1. 3 minus 1 is 2. So x sub 1 is equal to 3 over 2.
I have a question.
Yes.
If f of x equals s cubed minus x or s cubed minus x minus 1.
Right. Because in order for us to use our formula, this formula, we had to make f of x equal 0. So it has to be equal to 0. So since it equals 1, we move the 1 over, get it equal to 0. Now this is our function.
We got the one. Unless it says cross.
Actually, when actually, yeah.
Sorry.
Yeah. It's because y equals 1. That's where that equals. All right. So now this is our next input. And if we want to see f of 3/2, no, tab 2. (27/8), 12/8. 15/8. So that's our first one. So our next interval begins with 3/2. So x sub 2 is equal to x sub 1 minus f of x sub 1 over f prime x sub 1.
Twelve minus eight,
Well, what?
12 minus eight, where's that from?
Because to find out where our value is, I can plug it back into our original equation. This is 3/2, and that's 3/2. 3/2 cubed minus 3/2. 3 cubed is 27. 2 cubed is 8. In order to subtract these, I have to have a common denominator. Denominator is 8.
15/8 is x fixed, right? Fixed.
Well, that's my f value. So I'm trying to, this is gonna be close to 2, it's 1.8, 1.9. We're gonna keep on going until we get closer to 0. So the next one, we use, this is our x1. 3/2 minus f of 3/2 divided by f prime of 3/2. F of 3/2 is 15/8. F prime at 3/2. F prime was 3x squared. Three over two is 9/4. Makes it 27/4 minus 4/4 makes it 23/4. (15/8), 4/23. So this will be 23/23. 72 minus 15. 57/23. Well, we're not looking at 0, we're looking at 1. We're looking at when this number gets close to 1. Because we're trying to cross the y=1 horizontal axis. Now, when we do iterative methods like this, doing it by hand is painful. That's why we use computers, Excel, to do this much easier for us. So we would keep on doing this over and over and over until our number gets close to 1. Any questions so far?
So, okay, so you started out at x0
Equals.
1 across the.
Well, we just pick a number. Yeah.
It's-
A lot of times 0 won't do us any good because we'll keep it at 0.
Right.
So we'll use something will make it move. Because whatever we pick, if it's too high, if it's too low, it'll make it go higher. If it's too low, it'll make it go lower. And that's the whole beauty of these things, is we're gonna find the next x value. We plug that into our equation. Good. Now, whatever this x value gives us, put in the next one to find the next one, plug that into our, and then eventually we're gonna get closer and closer and closer to 1, because that's what we're looking at when we cross it. So at what x value will it cross the y-axis 1? And that's what we'll be looking for. So we'll keep on going to 6 or 7, 8 steps till I get closer, because each time this number, this f of x number, will get smaller and smaller. It'll go from 1.8 to 1.6 to 1.4, 1.2, 1.1, and then keep on going to get 1.0. Yeah, well, yeah, I see, but these functions are pretty straightforward, and easy, but no, and I've done it in graduate school, we went over it in almost millions of times. Till it gets close to 0. Because yeah, then you have to decide at what level, how many zeros. This is called the level of accuracy, the degree of accuracy. Is 25 zeros good enough? Not for science.
Yeah.
So you want 1,500 zeros, so keep on going till we get that.
So when you would do that, would you have to sit there and like write all this out, or is that?
No,
like
what,
Excel?
that's, I'm glad you asked. Is that's the field my degrees are in, are numerical analysis. It's taking computers, programs, writing programs to make this stuff work. And before you do anything, is you always make sure it works by hand first. You do it first, like 4 or 5 by hand, run your program, compare the answers, and then if that works, let it go. Let it work forever.
It's always fascinating to me how somebody at some point in time came up with this, and was able to come up with it by hands. But then now in the modern world, we take for granted that you just plug it in.
Plug in a computer, it works.
Right, exactly.
Okay,
I do with quite a lot of numbers, studying graphs and the stuff that work.
okay, and that's what numerical analysis is. So now we're gonna get a term we haven't used before. Convergence. Convergence. What this does is if a function converges, it approaches a specific value. And this approaches, that's our approximation. So like, if we look at this function, as x goes to infinity, the function approaches 0. So it converges to 0. The opposite of converging would be right. This function. As x goes to infinity, our function also goes to infinity, so it diverges. It doesn't go to anywhere we want to specifically. So in reference to this with Newton's method, if it converges, approximates an x-intercept, then it converges to that value. And that value is a root. So if a function, if Newton's method converges, it always converges to a root, and a root is the x-intercept. Any questions so far? But if you want to next time, I don't want to do it now, but we could start playing with Excel to learn how to do that. Yeah, we'll use that when we have more free time. All right, there's that one. So that's it for chapter 4. Now we can start chapter 5.